Okay, so this is similar to the last problem. You want to find the tangent line to this curve. And again, we're going to use the fact that the gradient is perpendicular to the tangent lines. So let's first try to get a vector parameterization. We'll get two different equations for the tangent line. We'll get a vector parameterization, and then we'll get the normal equation. Remember, the normal equation is the ax plus by equals c equation. Okay, so let's do the vector parameterization. Remember, we need a point on the line and a direction vector. So to get the direction vector, we're going to start by finding the gradient of f. So let me first, just so that we're all on the same page, let me tell you what f is. So again, we have a function f of xy. This is equal to y times 2 plus sine of xy. And we're looking at the level set when this is equal to 1. The gradient is perpendicular to the level curves. So then when we want the vector parameterization, the direction vector is going to be any vector that is perpendicular to the gradient vector. So the gradient of f, and again, similar to the previous problem, I'll let you compute this on your own. The gradient of f evaluated at xy, this is y squared cosine of xy, and the y component is 2 plus sine of xy plus yx cosine of xy. And at the particular point that we care about, the gradient of f evaluated at 0, 1/2 is 1/4, 2. Okay, so then any vector, so if you want a vector parameterization, remember we need two things to do a vector parameterization. We need a point on the line, which is 0, 1/2. There's obviously infinitely many points on the line. We just need any point. We're given 0, 1/2, so that's what we're going to deal with, use, plus t times a vector that is parallel to the line. Well, any vector, we just need, again, any vector that is parallel to the line. So we'll just find some vector that is perpendicular to the gradient vector, and the easiest one is -2, 1/4. Okay, so this is a vector parameterization of the line. Now, if you want the normal equation, so let me just tell you this is the vector. On an exam or something, I would tell you which one that I want. But for this, it's a practice exam. I'm just going to do both of them. So remember that the normal equation is ax plus by is equal to c, where ab is a vector. This is perpendicular to the line. But we know the gradient vector is perpendicular to the line. The gradient vector is 1/4, 2. So then 1/4 x plus 2y is equal to c. And how do you figure out what c is? Well, you just plug in the point. Any point, you plug in any point on the line. We're going to take 0 and 1/2. And if you do that, you get that 1/4 0 plus 2 times 1/2. This is equal to c, and that's equal to 1. And so the normal equation is 1/4 x plus 2y is equal to 1. So notice that at least in R2, when we're finding the normal equation for a line, we need a point on the line and a point perpendicular, and a vector perpendicular to the line. So we still need these two pieces of information. Because in R2, once you know a vector that's perpendicular to the line, you also know a vector that's parallel to the line. So essentially, we need the same information, just in slightly different form. And I'll let you think about that. I also want to show you a Desmos graph. So I know in the last video I said that I wasn't going to go into as much detail, but I think it's just, I think it's so nice to be able to see this pictorially that there's no reason not to. So in red is the function that we're graphing. This is the curve that we are looking at. And then we want to look at the tangent line at the point x is equal to 0 and y is equal to 1/2. And that's what this blue line is here. So this is the point that I'm circling now. This is the point x is equal to 0 and y is equal to 1/2. And the blue line, this is the normal equation for the tangent line that we just came up with. And you can see clearly that the blue line is the tangent line. And if you zoom in closer and closer and closer, the curve and the line get closer and closer to each other, which is exactly what the tangent line does. Remember, the tangent line is the best linear approximation to the curve at that point. Okay, that's all I got for this problem.